I can't wait to go film my calculus project.
Nice motorcycle, dude.
Thanks, it's new.
Pricing terms and 531.
Woke up on it, go to like this morning, but I think I'll be okay.
Oh my gosh! I wonder how much force that water is exerting on that motorcycle.
Hey, I can show you.
So let's take a look at what hydrostatic force is. The hydrostatic force on an object is equal to the density of the fluid that it's in, which we represent with rho, times the surface area of the object, multiplied by the depth that the object is at. So the first thing we do is we determine the shape of our object. So say it's a triangle, like so. First, we have to draw representative rectangles to show the area and depth at which the force is being applied to the object. They have to be horizontal because if they were vertical, the depth would be different at each part of the rectangle. In order to determine the length of our representative rectangle, we have to draw axes on our diagram in order to determine the equation of these lines. So since it's a triangle, I'm going to put my axes right here so that the origin is at the tip of the triangle. This makes it really easy to determine the slope of our line and find an equation that shows this side of the triangle right here. In order to make our calculations easier, I'm just going to cut the triangle in half and only solve for one side and then double our answer in the end. So we can ignore this whole side right now. So since we have our representative rectangles, we're going to pretend that there's a whole bunch of them going up and down our object. We'll call this one the ith rectangle. We have to determine the area of this rectangle, which is equal to the area of a rectangle is equal to length times height. So the length in terms of y times delta y. The reason that we use L in terms of y is because the length of our rectangle is the same thing as the distance x from the y-axis. D is actually going to be the depth of the rectangle from the top of the water. It is also going to be in terms of y because the depth is a y value. So the depth, we'll call it the h for height in terms of y. So now we can use these equations and substitute them into our force equation. Force equals rho times h in terms of y times L in terms of y times delta y. This is the force of just one of our representative rectangles. So what do we do now? Now we substitute it into this limit slash summation. I'm recording. I equals 1. This goes to n. By the way, this equation is all in terms of the ith rectangle. Rho times h. This can be rewritten as the integral from a to b h of y L of y dy. All that multiplied by the density of the fluid. This will find the hydrostatic force across the entire object. Alright, so now that we know how we derive the equation, let's take a look at the motorcycle example. So say our water line is here. And let's say that the motorcycle sunk so that the front wheel is facing straight downward. And let's generalize the shape of it as this rectangle. So let's start by picking an axis. I'm gonna say, let's make the origin down here in this corner. So my origin is 8 units underneath the water. And my rectangle is a 3x6 rectangle. So rho is a constant, it doesn't change. Our limits, A and B, are going to refer to the bottom and top of the object. So we'll go from 0 to 6. The height in terms of y is simply 8 minus y, because you do top minus bottom. That'll give us the depth of our representative rectangle. So if you notice here, our rectangle is at 3, 8 minus 3 is 5. So this rectangle is 5 units underneath the water. The length in terms of y is just a constant 3. So we're just going to multiply it by 3. And then dy. Now rho is just the density of water, which is a constant. It's 62.4 times the integral from 0 to 6, 8 minus y times 3 dy. And that's how you set up the integral. And the units are in pounds.
Alright, that seems simple enough. I'll try one myself. So, the motorcycle could potentially look like a triangle. So we'll use the same equation to solve for the hydrostatic force, which will be the density times the integral from A to B of the height times the length, dy. So once again, we will split the triangle into 2 halves to make it simpler. We will make the axes go through the point of the triangle for convenience. We don't want any y-intercepts. The equation for this line right here is going to be y equals 3/2 x. But since our representative rectangles are horizontal, we need to solve for the x. So it will equal x equals 2/3 y. To solve for the hydrostatic force of this triangle, we will use the density, which is always 62.4 for water, and we'll do the integral from 0 to 3. The height will be 5 minus y, which represents 5 minus y as it changes, and the length will be right minus left. So we've solved for the function here. It'll be 2/3 y minus 0, so we'll just keep it as 2/3 y, dy. For a shape like this, I would complete it so it looks like a triangle, and then I would place the axes where the point would be. Then we would use the equation of this line right here, which would be y equals x. We have to solve for x, so it would just be x equals y. But once again, our limits of integration would be slightly different. It would go from 1 to 3 instead of 0 to 3.
So for a circle, the best place to put the axes is right here in the center. Because then your equation for the circle is going to be x squared plus y squared equals r squared. So when you solve for x in terms of y, you're going to get x equals plus or minus the square root r squared minus y squared. And we can just take the right half of the circle, so we can just ignore the negative part, and it's x equals the square root of r squared minus y squared. Now we know how to do hydrostatic force problems.